Hi, welcome to a new session of control systems. In today's class, we are going to see time response analysis, and this particular class we are going to treat as class 3, where you can see an input R of t, which is taken as step input when it is given to a second order system under underdamped system, how the output C of t is obtained. So that is our interest of this particular class. So we'll start with the basics of second order system. You can see a closed loop second order system is shown by this particular block diagram, where you can get the transfer function in the terms of C of s by R of s, which will be given as omega n square by s square plus 2 zeta omega ns plus omega n square, where omega n is known as undamped natural frequency and zeta is treated as damping ratio. Now, for undamped system, we have seen in our previous class, we have to make zeta equal to 0. And for underdamped system, the variation of zeta is from 0 to 1. For critically damped system, the value of zeta is exactly equal to 1. And for overdamped system, the zeta value is greater than 1. Now, the characteristic equation for second order system is given by s square plus 2 zeta omega ns plus omega n square. Now, this particular equation can be solved in terms of its roots by s1 s2 with the standard formula of minus b plus or minus under root of b square minus 4ac by 2 into a. With this, I'm going to get the value of s1 s2, which is given by this particular equation, which is minus zeta omega n plus or minus omega n under root of zeta square minus 1. Anyhow, when you are going to deal with underdamped second order system for unit step input, so we have to consider the standard transfer function. We are treating this one as equation 1. And for underdamped condition, the range of zeta is from 0 to 1. So we are making use of this characteristic equation, and since the zeta is less than 1, it is understood that zeta square will be also less than 1, and 1 minus zeta square is always a positive number. So what we are going to do, we are going to make the alterations in this equation too. You can see I have taken minus inside this square root as minus 1, and we have changed this zeta square minus 1 as 1 minus zeta square. I can remove this minus 1 outside, and it can be changed to minus zeta omega n plus or minus j omega n under root 1 minus zeta square. So this can be treated again as minus zeta omega n plus or minus j omega d, where omega d is known as the damping natural frequency. So the damping frequency is, in terms of natural frequency, is given by omega n under root 1 minus zeta square. After this, treating these equations from 1 to 5, we are going to take the input, which is nothing but unit step input. In time domain, it is given as r of t equal to 1, whereas in frequency domain, it changes to r of s is equal to 1 by s. And we are going to make use of this transfer function. We will replace this r of s by this 1 by s term. So when that is done with the help of partial fractions, I can change this to a by s plus bs plus c by the characteristic equation, which is shown over here. Now, equation 6 can be solved in terms of constants a, b, and c. With the first value a, I'm going to get the value as 1, and b and c can be obtained from the equating method. So you can take the s square term and s term, and you can equate to the LHS and RHS on both sides. With that, we are going to get the value of b is equal to 1, which is nothing but equating the coefficients of s square. Similarly, we are going to get the value of c, which is equal to minus 2 zeta omega n. Just substitute these values of a, b, and c. We are going to get this particular equation. Now you can see I have taken this minus outside, and this becomes s plus 2 zeta omega n by this particular equation. Now equation 7 can be elaborated like this. You can see I have taken this 2 zeta omega n. I have taken individually zeta omega n, and denominator I have taken zeta square omega n square minus zeta square omega n square in the addition and subtraction mode for denominator condition. With this, I can replace the formula into s plus zeta omega n whole square. So that is what I have done here. You can see s plus zeta omega n whole square, and again I have taken omega n square common, and I have taken 1 minus zeta square as the common value of these two parameters. Now you can see this equation is again reframed as 1 by s minus, you can see I have taken s plus zeta omega n as one term divided by this particular denominator. This omega n square of 1 minus zeta square can be written as omega d square. Similarly, this omega n with zeta n can be divided by this particular denominator, that is s plus zeta omega n square whole square plus omega d square, which is nothing but the replacement of omega n square of 1 minus zeta square. Now this particular parameters is multiplied and divided by omega d, and you can see this equation 8 is framed, and the equation 8, the denominator I have taken omega d, which is equal to omega n under root of 1 minus zeta square. Now carefully observe, I'm trying to reframe the equation 8 in terms of equation 9 like this. You can see just I have changed the values of the omega d with omega n, and now I'm just reframing this equation 9. You can see over here I have taken this omega d on this side, zeta omega n on this side, okay, and the denominators are matched accordingly. Now you can see we have here omega d by omega n under root of minus zeta square, okay. Now I can carefully remove this omega n, right, and zeta can be taken on this side, omega d can be taken on this side, such that equation 10 is free. Why we have done this? Now you can see this formula resembles the Laplace formula, and this formula also resembles the Laplace formula. One is in cosine term and one is in sine term. So applying Laplace inverse to this equation 10 and making use of this particular Laplace uh, actual parameters of Laplace of e to the power of minus at sine bt, which is given by this particular value, and Laplace inverse of s plus a by s plus a whole square plus b square is given by e to the power of minus at cos bt, and we know that Laplace inverse of 1 by s is nothing but equal to 1. So I'll make use of these three Laplace equations, and I'll frame these three according to the Laplace inverse of this equation 10. So you can see I have framed the values and I have obtained in terms of e to the power of minus zeta omega n t cos omega dt minus zeta by under root of 1 minus zeta square e to the power of minus zeta omega n t sine omega dt. Now you can see the common terms are taken on one side and equation 12 is framed. Now I can make use of this triangle where I have zeta on the adjacent and 1 minus zeta square as opposite. So with this I can get the values of sine theta and cos theta. So wherever I have this parameter, there is 1 minus under root of 1 minus zeta square, I can replace it by sine theta. Similarly, zeta can be replaced by cos theta. So that is what is done in equation 13. I hope you understood how we have framed equation 11, 12 and 13. Now just rearranging this equation 13 in terms of sine A cos B and sine B cos A formula, such that sine A plus B is equal to sine A cos B plus cos A sine B. So with that I'm going to frame equation 14, and this particular equation is nothing but 1 minus e to the power of minus zeta omega n t by 1 minus zeta square multiplied with this sine term. So it's an exponential term and it's a sine term. So when you apply this r of t as input to the second order system under underdamped conditions, you can see we can get the oscillations and they are getting damped out and they are reaching to the constant 1 condition. So this is the output response of c of t. Now what happens if I take the value of zeta which is equal to 1, then it becomes a critically damped system. So the same analysis, we are taking the standard transfer function equation and we are making zeta equal to 1. When zeta is made equal to 1, this formula changes to s plus omega n whole square, and we have r of s which is equal to 1 by s, and again I can get the values of this particular partial fraction in terms of a, b and c. So that a, b and c can be obtained by this equation 1 Roman 1, where I have taken the value of s equal to 0 such that a's value is 1, and expanding equation 1 and taking the powers of s square and s power term, I am going to get the value of b as minus 1 and c as minus omega n. Just replacing the values of b and c, and I'm going to get the equation 3. I'm applying the Laplace inverse to this equation 3, and I'm going to get the value as 1 minus e to the power of minus omega nt minus omega nt multiplied with e to the power of minus omega nt. Now this is from the standard Laplace equations formulas it is derived. Now equation 4 is framed with 1 minus e to the power of minus omega nt 1 plus omega nt. What if I substitute the value of t equal to 0? I'm going to get the value as c of output as 0. And what if I take the highest value, that is infinity? I'm going to get the value of c of infinity which is equal to 1. So for a particular input, I'm going to get the output in this fashion. So you have observed that under underdamped condition we have the damping out oscillations and we reach it to the constant, whereas for the critical damped system the output is reached quite quickly, responding to the input. So that is the difference between critically damped system and underdamped system. So that's all for today's class. I hope you like this particular video. Please share among your friends, subscribe to this channel and press the bell icon for the future notifications. Thank you.